Greetings everyone, by request, here's a video on differentiating with respect to different variables and trying to just get a handle on some things that we've been doing. And I want to go back and remind you, first of all, where this idea of differentiating came from. We started talking about differentiation really before we even started using the word about slopes. We started talking about slopes of tangent lines. But you've been talking about slopes of lines for a long time, and so we were embedding in this discussion your prior knowledge and using your prior knowledge to help generate the concepts way back on day one of what we meant by a tangent line and how to find what one is at a certain point. And so we started by taking slopes of secant lines and then using those to approximate the slopes of the tangent lines, and then making the secant lines better by moving the second point closer to the point of tangency. But that's not the point right now of this lecture. What I want to remind you about is, when we were calculating slope, you would work on, even back in algebra, change in y over change in x. And this was the foundation of the idea of a rate of change. Remember, one of our other interpretations of differentiation. And so this lays the intuitive understanding of what you're supposed to bring when understanding what a derivative is. In calculating the slope, what we're trying to measure, what we're trying to see is how is y changing as x changes. So we're measuring how y is changing for different changes in x. And since when we were talking in algebra about the slope of a line, and that slope never changed, we'd say, well, if x increased by this amount, then we could predict how much y would increase by, and things like that. Now in calculus, when we're dealing with nonlinear curves, the slope the slope of the curve will change in different, depending on where you are in relation to the curve. So at different points, we'll have different slopes of tangent lines. And so we started getting into this idea of wanting to know the slope at a certain instant, even though we knew that the slope was going to change somewhere down the line, because knowing the slope at an instant would give us certain information that would be helpful to us. All right, nonetheless, the idea is that we were measuring how fast y was changing as x changed. Eventually, then we got into the differences between average rate of change and instantaneous rate of change, where we're again measuring for average rate of change. We were measuring how fast something was changing with respect to how big the interval was. Okay, average rate of change was over an interval. And then for instantaneous rate of change, we wanted to shrink that interval down to see if we can figure out how fast something was changing at some instant. But again, this goes back to seeing how one thing changes as something else changes. So in our notation, dy dx, taking a derivative, we're doing the same thing here. This is the notation was designed to appeal to our delta y over delta x that we saw a little bit ago. So Leibniz, when he came up with this, he was saying we want to measure how y is changing, the quantity y is changing as x changes. But here, instead of using deltas, which appeals to the notion of on an interval, he used d, which is supposed to be that intuitive understanding of delta changing into a d as the interval got smaller and smaller and smaller. So the delta and the d still had an echo of each other, but they weren't exactly the same thing. Keep in mind that the notation dy dx represents measuring how y is changing as x changes. But then we separate out this d dx part, and we call this the differential operator. So this is actually equivalent notation as to putting the y in a set of brackets or parentheses that follows d dx. So then we've now changed this set of symbols right here into like a plus sign or a minus sign or just some mathematical operation notation. So this notates the operation of taking the derivative. And then we also have even lazier shortcuts for this, and we call it y prime, which is a little less instructive because we don't know with y prime if we're differentiating with respect to x or some other variable. Now, the issue people were asking me about is dealing with differentiating with respect to different variables. And so let's see if I can show you some contrast here. If I'm differentiating with respect to x cubed, then there's really no big issue here in the sense that, as we talked about before, we have the same variable in the expression x cubed that we're using to differentiate with respect to. But keep in back of our mind that we're still trying to measure the rate of change of an output with respect to the change in input. And so that y cubed represents the output. X is our input, x cubed is the output. I think I said y cubed a moment ago. I apologize for that. The input is x, the output is x cubed. So implicitly in this statement here, we should keep in mind that y is equal to x cubed. And so that when I differentiate, I am still differentiating, the expression y, but I just know what the expression is in terms of x. And so the usual rules, typical rules would apply here. Whoops, that would be squared. And the derivative would be 3x squared. But now if I change and I want to differentiate with respect to some other variable, t, and I'm still using the same expression x cubed is still an output. But here there's a different issue. The input is supposed to be t. If you look up here in the previous example where the x cubes matched, up here, x was my input, x cubed was my output. But down here, t is my input, and x cubed is my output. There's a disconnect there because I don't see exactly how t is being used in the expression x cubed to generate the output x cubed. So what's really underlying what's going on here is that x is a function of t. Meaning when t changes, x is going to change. And then when x changes, x cubed is going to change. But see, I don't see that connection. There is no instructions in the problem here specifically telling me how the changes in t affect the changes in x. If I had that data, then I could apply it. Maybe I knew that x was equal to 2t. If x was equal to 2t, then I could replace the x in my expression here with 2t, and then I could simplify it and then apply the rules. But since I don't know that, I still have to account for it indirectly, even though I don't have the direct information of what that change is. And so what we do, since x is a function of t, we have to think in terms of the chain rule. My outer function is cubing something. My inner function is x of t. But I don't know what that is. They're not telling me. So when I take the derivative here, I still have to take the derivative of the outer function, which is going to be 3x squared. And then I have to multiply it by the derivative of the inner function. And the inner function is x, so the derivative of x with respect to t is dx dt. Now we get lazy. We want to write 3x squared. It's actually not being lazy. That's a little too harsh of a criticism. But we want to write it more efficiently, so we'll say 3x squared times x prime, just with an understanding that x prime is the derivative of x with respect to t. So the key point to understanding here is that when these variables are different, what's either maybe directly stated, or if not directly stated, it is implied that the variable in my expression, here inside the x cubed, that variable in there is changing as t changes. And so I have to account for that change when I take the derivative. So if I have, the derivative with respect to z of x times y, an expression we've taken the derivative of quite a bit lately, but some are still struggling with, I have to pay attention and say, well, z and x are different, z and y are different. As z changes, x is going to change. As z changes, y is going to change. And so I have to account for those changes when I take the derivative. And so when I apply the product rule to this, because they're different, when I take the derivative of x with respect to z, and if you want, you can just write x prime, that's going to measure how x is changing as z changes. All I have is notation for it. I don't have a specific expression for it. By the product rule, then I'd multiply by y, and then I would add, and then I'm going to take the derivative of y with respect to z, which we can call y prime, and then multiply that by the first factor x. Because the variables are different. If they were the same, then the derivative of z with respect to z would be 1. Or if I had z to some power, then I know I would apply the power rule, or some other rule that we already know on how to take the derivative. The key is to see if they match or if they're different. If they match, then you apply the rule as is, and if they're different, then you have to remember that the variable that's in the expression is changing as the variable that we're differentiating with respect to changes, and so we have to apply the chain rule. One last little thing on notation. A mistake that I've starting to see crop up again, and I mentioned this a while back, but just as a reminder, if I'm asked to differentiate this equation here with respect to x, so I may want to find an expression for y prime or something like that. What I don't want to do, this is wrong, I don't write dy dx of x plus y squared equals dy dx of 3. The reason why I don't do this is because remember the differential operator d dx. That acts on whatever is next to it. But here, in this expression that we've written, the d dx has next to it y. So here, this notation means that d dx has to be applied to y, or I have to differentiate y with respect to x. And then, well, at that point, the brackets meaning, the meaning of the brackets is not the same as it is down here in this picture. Down here, the d dx is applied to whatever in the brackets. Since d dx is applied to the y, the brackets then become just meaning a product. You're multiplying here by it's a grouping symbol, so you're going to multiply the whole dy dx times x plus y squared. You never actually take the derivative of x plus y squared. We don't write it like this. Over here, I don't take on the right hand side, the d dx is being applied to y. It's not being applied to the 3. I never end up with 0 on this side. That's not the correct way of writing this down. The correct way of writing this down is to put d dx of x plus y squared is equal to d dx of 3. Now, since there's nothing in the space right next to the d in the numerator there, d dx applies to what's in the brackets. d dx applies to what's in the brackets. And so I would end up with 1 plus 2y y prime, and that's real sloppy, sorry about that, 2y y prime is equal to 0, and then I can continue the problem to solve for y prime. So please stop making that mistake if that's you. Go study.